this address I will introduce two irrigation concepts, namely measured irrigation and evaporative irrigation. I will then discuss the significance of these concepts for water efficiency and energy efficiency for various irrigation applications. Firstly, I'll define these two very important terms. Irrigation is referred to as measured if the volume of water delivered to each plant is controlled directly without the need to control the flow rate or the duration of the irrigation event. You might want to just think about that for a minute, because that is a very unconventional approach to irrigation. The second definition is irrigation is referred to as evaporative if the application rate to each plant throughout the year is proportional to the net evaporation rate. That's evaporation rate minus rainfall rate. Conventional irrigation systems use a timer or a controller to control the opening and closing of solenoids in order to control the duration of the irrigation event and the frequency of irrigation. The volume of water delivered to a plant during the irrigation event is controlled by controlling the flow rate from the emitter and the duration of the irrigation event. The acceptance of this paradigm for controlling irrigation has led to the development of the pressure compensating dripper, whereby the flow rate from the dripper is relatively constant for a range of water pressures. With measured irrigation, the volume control paradigm is completely different. For measured irrigation, the volume of water delivered to a plant during the irrigation event is controlled directly, so that one does not need to control the flow rate and one does not need to control the length of the irrigation event. Experienced irrigation practitioners are often sceptical of an irrigation methodology that does not need to control the flow rate. I will therefore request that you restrain your scepticism and listen carefully to what I say. The conventional volume control paradigm requires control of two variables, namely the flow rate and time. Measured irrigation requires the control rate of a single variable, namely volume. Once you change your focus of attention from flow rate and time to volume, the design of an irrigation system can change significantly. I will now discuss the design of an unpowered evaporative measured irrigation system with two sectors. I will use this schematic diagram to demonstrate the basic principles and advantages of evaporative measured irrigation. Firstly, the water supply may be either pressurised or gravity feed. The importance there is the emphasis upon gravity feed. The emitters in each sector should be at approximately the same level. Here we have two levels, as you can see. For each sector, a control nozzle drips water into the evaporator during the irrigation event. You can see there with the red arrow where I'm pointing to the control nozzle, one for each evaporator. For any combination of emitters and control nozzles may be used. However, to keep things simple, let us assume that all the emitters and control nozzles are the same, and so they will all deliver the same volume of water during the irrigation event. 5. One needs to estimate the net evaporation in millimetres for the location for the hottest dry month of the year. For example, in Adelaide, the net evaporation is about 267 millimetres in January. This information is available from the Bureau of Meteorology. One needs to choose the desired number of litres per week per dripper during the hottest dry month of the year. This is a very important step, because in this step you will take into account all of the parameters such as soil type, evapotranspiration, leaf area, and any other factor that's relevant in deciding how much water the plants need during the hottest dry month of the year. the following formula is used to calculate the surface area of evaporation required to deliver the desired number of litres per week per dripper during the hottest dry month. I won't go into the formula, but you work out what is the desired surface area of evaporation. Suppose that many different... Now, I'll just go back to that slide. So you've decided on the surface area of evaporation. You then need to choose an evaporator with that appropriate surface area of evaporation to ensure that each dripper has the desired application rate in litres per week for the hottest dry month. So you can see in the evaporators in that diagram, and one chooses them to have a surface area to deliver the amount of water per week that you require. Now suppose that many different emitters are used, and for each emitter one knows the nozzle ratio. The nozzle ratio is a critical concept in measured irrigation. It's the ratio of the flow rate of an irrigation nozzle to the flow rate of the control nozzle. Next step, a level line is marked on the inside of the evaporator about 3 centimetres below the overflow level. So you can see the level line marked with a red arrow. For each sector, open the valve when the water level is approximately 1 centimetre below the level line, and close the valve when the water level reaches the level line. The cycle continues indefinitely. So here we have a very simple system, very low tech, extremely low tech system, gravity feed, which delivers the appropriate volume of water per litre to each plant just by turning off and turning on a tap. It's that simple. I'm now going to discuss some of the advantages of this particular model of unpowered evaporative measured irrigation. I have a total of 9 advantages. We'll go through them one at a time. Firstly, you save more water by controlling the application rate for each plant during the hottest dry months of the year, taking account of all relevant factors such as evapotranspiration, soil type and leaf area. Advantage 2, you save more water by allowing the prevailing weather conditions to control the variations in the application rate for each plant throughout the year. The irrigation is evaporative, that is, the application rate for each plant is proportional to the net evaporation rate. Now, I just should emphasise at this point, we're not using evaporation to decide how much water each plant gets. We decide how much water each plant gets by step 1, by choosing the required application rate during the hottest dry month. But then we allow, once we've chosen that figure, we allow the application rate to vary throughout the year according to the net evaporation at the various times in the year. Advantage 3, application rate is not affected by the water level at which the irrigation starts and the water level at which the irrigation stops. So we have a very robust system where you don't have to be very careful about when you turn it on and when you turn it off, because the system is robust and it doesn't matter so much when you turn it on and off, you will still get the same application rate. 4, you can adjust the irrigation frequency by adjusting the water level at which the irrigation starts. For example, if you require more frequent irrigation with less water, then start the irrigation when the water level is less than 1 centimetre below the level line. And on the other hand, if you require less frequent irrigation with more water, then start the irrigation when the water level is more than 1 centimetre below the level line. 5, for those months of the year when the rainfall exceeds evaporation, the water level will be above the level line and so there is no irrigation. 6, gravity feed irrigation requires that the head of water in the water tank is higher than the emitters. As the water tank empties, the flow rate at the emitters will decrease. This would be a problem for conventional irrigation systems because they need to control the flow rate. Now, because we've abandoned that requirement of controlling the flow rate can change as much as you like because we don't have to control it. We are controlling the volume of water directly. 7, very important, measured irrigation does not need to be pressurised and so it is much more energy efficient, and also no hose clamps are needed. For conventional gravity feed systems in developing countries, which of course use gravity feed because it's all that can be afforded, a minimum head of water is recommended, usually greater than 1 metre. With measured irrigation, it is far more energy efficient because the head of water required is much lower. And finally, emphasising that evaporative measured irrigation is an example of a low-cost, simple technology with a high level of control over the application rate to each plant. I now want to go through some particular applications of measured irrigation, and these are the 5 I'll try and get through. The first one is low-cost measured irrigation for smallholders in developing countries. And when I'm talking about low cost, I'm talking about extremely low cost. The second one is measured irrigation from a rainwater tank. The third is upgrading drip irrigation to measured irrigation. So this is taking a conventional pressurised drip irrigation system and how that can be upgraded to measured irrigation. The fourth is measured irrigation for seedlings in nurseries. And finally, I'll be looking at solar-powered multi-sector measured irrigation, of which there are many established applications in community gardens in Australia. So the first thing we're going to be looking at is low-cost measured irrigation for smallholders in developing countries. And the first, I'm going to use videos for this because there's a lot of images I want you to see. My name is Dr. Omodei, and I'd like to show people who are using drip irrigation how to improve their watering efficiency and to reduce water consumption. All that's needed is just a bucket. Primarily, I want this video to be for landholders or smallholders in developing countries, and so I'm going to assume that the irrigation system is not pressurised and that it's gravity feed. Part 2, the evaporator. Then, while my garden is being irrigated, water's going to drip from the control nozzle into the evaporator, slowly filling the evaporator. Okay, the water level has now reached the level line, so we turn off the tap. And that's the end of the irrigation. And that's my cat. We now need to wait until water has evaporated from the evaporator. And it may take a couple of days. Part 3, irrigation frequency. And when the water level has evaporated so that it's 1 centimetre below the level line, then we start the irrigation again. Notice that the rate at which the water evaporates depends upon the weather conditions. When it's very hot, the water will evaporate more quickly. And when it rains, water will enter the evaporator, and so the start of the next irrigation will be late. I now want to move on to the next video, which is measured irrigation from a rainwater tank. Introduction.
This video will answer 3 questions. What is the simplest way to water your garden from a rainwater tank? Why is this information not available from any irrigation supplier? And how can the irrigation system be automated using a solar panel?
Part 2, nozzles.
For gravity feed irrigation, an ideal emitter is a short cylindrical tube or nozzle where the diameter of the nozzle is sufficiently small to ensure that water is emitted very slowly. I recommend using short, blunt stainless steel needles. The nozzles are colour-coded to indicate their internal diameter. Position a yellow nozzle so that it drips water into the box. The nozzle is called a control nozzle.
Part 3, application rates.
Provided the pressure is the same at each nozzle, the table shows the average number of litres per week delivered by the 9 different nozzles. The table is based on the annual evaporation and rainfall in Adelaide. Black, 0.8 litres per week. Green, 1.5 litres per week. Yellow, 2.3 litres per week, etc. all the way through to olive at 28 litres per week.
Part 4, irrigation industry.
Irrigation companies worldwide have invested billions of dollars in pressurised irrigation. Gravity feed is a potential threat to this investment. Suppose that you walk into a local irrigation supplier and say that you would like to irrigate your garden using a rainwater tank. One of the first issues raised will be the choice of pump, and from that point forward, gravity feed will never be mentioned.
Part 4, automation.
How can the irrigation system be automated using a solar panel? You will need a solar panel, a 12-volt battery, a charge controller, a level sensor, a valve controller, and a solenoid valve. When the water in the evaporator falls below the low probe, the irrigation commences. When the water level reaches the high probe, the valve controller closes the valve and the irrigation stops.
Part 6, irrigation frequency.
To change the irrigation frequency, adjust the gap between the high probe and the low probe. Measure the control volume. This is the volume of water that drips from the yellow control nozzle into the evaporator to raise the water level from the low probe to the high probe.
Part 7, nozzle ratios.
The volume of water emitted by an irrigation nozzle is the control volume multiplied by the nozzle ratio of the irrigation nozzle to the yellow control nozzle. For example, if the control volume is 1.5 litres, then the table lists the nozzle ratios and the corresponding emitter volumes.
Now, the next video we're going to look at is for upgrading drip irrigation to measured irrigation, and this is for powered applications in developing countries.
This video is about the drip irrigation upgrade kit. The kit contains everything you need to substantially increase the water efficiency of any drip irrigation system connected to mains power. A drip irrigation controller is normally used to automatically control the irrigation of each sector in your garden. The drip irrigation upgrade kit contains a measured irrigation controller that will override the drip irrigation controller for one or more sectors. How to choose a suitable evaporator. 1. Use the measured irrigation nozzle selector tool to estimate the monthly net evaporation in millimetres during the hottest dry month of the year at your location. The measured irrigation nozzle selector tool can be downloaded from the measured irrigation website. For example, in Adelaide, where I live, the hottest dry month is January with a net monthly evaporation of 267 millimetres. 2. Choose the number of litres per week that you would like each dripper to deliver during the hottest dry month of the year. 3. You now need to choose an evaporator such that the surface area of evaporation equals the number of days in the hottest dry month multiplied by the number of litres per week per dripper divided by the net evaporation in millimetres during the hottest dry month divided by 7. The kit consists of the following
Components. We've got the level sensor with the 3 probes, we've got the measured irrigation controller, and we've got a 12-volt DC power adapter. So basically that's all you need to be able to upgrade a conventional irrigation system. The next video we're going to look at is measured irrigation for seedlings in nurseries.
I'd like to demonstrate a prototype for water efficient irrigation for seedlings. The prototype was installed at Providence Indigenous Plants in Adelaide. Pete, the owner, was looking for a way to reduce his water bill. This video is relevant for any seedling nursery where the cost of water is a major expense. The usual method of watering seedlings is with overhead spray, where most of the water is wasted. The prototype uses measured irrigation on a boom. You decide in advance how much water each seedling requires during the irrigation event, and measured irrigation will automatically measure the prescribed volume of water for each seedling. One of the challenges in the nursery is the scheduling of the controller to automatically water your plants without wasting too much water. With measured irrigation, scheduling is very simple. The irrigation frequency is controlled by the prevailing weather conditions.
And lastly, I'm going to look at some slides for solar-powered multi-sector measured irrigation. There's more than 8 community gardens in Australia, mainly in Adelaide, that are using this particular arrangement for measured irrigation. And I'll show you some slides for an installation at Sophie's Patch at Mount Barker in South Australia. Here I'm explaining the evaporator and level sensor. That's the evaporator and level sensor. You can see the white powder on there. That's because we're using bore water in this case, and it's got a very high salt content. So as soon as the water evaporates, it leaves a deposit of calcium. Here we have a flow splitter delivering water to 11 sectors. Each sector has its own separate control. A green control nozzle delivers water to the evaporator. These are the flow splitter nozzles available from measured irrigation, going from very small up to quite large. All the power needed comes from a 20-watt solar panel. The sectors following the contours on sloping ground. In this case there are 11 sectors. This is the vegetable garden sector, where the delivery mechanism is Netafim Landline 8 dripper line. A standard product for pressurised irrigation can be used in this case for gravity feed. In each sector we have a pressure monitored tube which indicates the head of water in the sector, and that's a typical level of pressure you will be using for measured irrigation, something like 40 centimetres, these heaps. Here I am demonstrating measured irrigation at an open day at the Sophie's Patch Garden. And now, finishing off, the accuracy, I'll talk about a little bit about the accuracy and uniformity of measured irrigation. Published trials of measured irrigation have demonstrated accuracy greater than 95% and uniformity greater than 95%. This information is, amongst other places, is available by publication in January this year in Irrigation Science. Finally, I have produced a transcript of my talk today, so if anybody wants a copy of that, they can approach me any time during the conference. Thank you very much.
Thank you very much, Brian. Are there questions? Yeah. Please.
Just slide, yes.
Is it a slide? That one? No, that one.
The last one, before the last one.
Before the last one, okay. That one?
Previous one.
That one? Before?
Yes. I want to ask about the accuracy and the precision. What's the difference between them?
Oh, with measured irrigation, you use the nozzle ratio to predict how much water will come out of each nozzle, right? And so with accuracy, we're saying how accurate is that prediction. And to measure the accuracy of a prediction, we will use the mean of all of the emissions and compare the mean of those emissions with the predicted emission, and that's the accuracy. Uniformity is what is not normally understood by uniformity. Uniformity is simply how uniform the flow rates are. It doesn't say how accurate they are.
Actually, I observed your slide. It's depends on your horticulture plot. So I asked about the question: is it possible to irrigate the field crop just like rice, wheat, and just a large area crop?
The problem of larger areas is one of cost, and the issues about whether to use drip irrigation or not for a larger area is the same issue when you look at measured irrigation. Think of measured irrigation as a refinement or an upgrade of drip irrigation. So for field crops, if you've decided that drip irrigation is too expensive, then measured irrigation will also be too expensive. Measured irrigation is really most appropriate for very small farmers who want to maximise, at low cost, the use of the water resource they have available to them, given that it doesn't require energy because of the fact that it's gravity feed, and so it's very, very appropriate for poor rural farmers who have a small crop for their family and to grow vegetables for the market. That's the ideal application of this technology.
Hope I appreciate this technology, sir. It's good. What about, is it possible to do the fertigation in the same drips?
Yes, yes, certainly. It's
only for irrigation or what fertigations? Fertigation also, there won't be any blockages?
Well, it's the same as drip irrigation. If you can use fertigation with drip irrigation, you can use fertigation with measured irrigation. There's no difference really in that sense.
Okay, that's an important question, right? So the likelihood to clog the nozzles or so is no higher with measured irrigation.
Well, there are a number of different choices for emitters, and for larger applications, I would be suggesting people use some commercial product like Landline 8, which has been on the marketplace for over 10 years, and the nozzles are very resistant to blogging because of the technology that's been developed. And so one can use these conventional, highly developed delivery systems, which are normally used for pressurised irrigation, which can also be used for gravity feed.
In India, we are having the system of irrigation called drip irrigation.
This is, yes, yes,
drip irrigation.
yes.
Where we are, limited quality and measured quality can be supplied to the crops. If you go, it depends mainly on the quality of water. If the quality of water is good, there won't be any blockages in the nozzles.
Yes.
If
The same issues. The issues, any issues you have to do with blockage with drip irrigation, you're still going to have the issues with measured irrigation. Measured irrigation doesn't address the issues of the nozzles and blockage. And you can use the same nozzles for pressurised drip irrigation or gravity feed drip irrigation. You can use the same nozzles for measured irrigation. So the nozzles are not an important part of measured irrigation. What's the important part of measured irrigation is that you only require very low pressure. And you only require very low pressure because you're not trying to control the flow rate from the emitter. It doesn't matter how long, and typically for measured irrigation, you might have the irrigation event might last for 4 or 5 hours. It'd be very, very slow because of the very low pressure. But that's not a problem because you still get the correct volume of water delivered to the plants, even though it may take a long time for that to happen.
Is that low pressure you mentioned, is that getting easier for the nozzles being blocked?
It's actually with low pressure. I'm not 100% sure on that one. I suspect that with low pressure they're less likely to get blocked, but I'm not sure. I'm not sure.
Thank you, Prof, for your presentation. My concern is on irrigation for smallholder farmers.
Yes.
You find like in my country where I'm coming from, these small vegetable farmers use like watering cans because they cannot afford the nozzles that
Yes.
water pumps. But in this case, they either use the watering can to do the watering of small gardens, vegetable gardens, and also they get a hose pipe, connect it to a water supply, then use the hand to regulate the flow.
Mm-hmm.
So in this case, how can you regulate the rate of flow so that you can maximize what they use?
When you talked about using watering cans, using watering can is by my definition measured irrigation because you've got the water in the can, you know how much is there, and you apply the water to the plants. It doesn't matter what the flow rate is, it doesn't matter how long you take to empty the watering can, you get the correct volume of water. So a watering can is a very, very simple example of measured irrigation. But when you start talking about getting a hose and controlling the flow rate from the hose, that's not measured irrigation, that's conventional irrigation. And so what I'm will be suggesting is that when you go to using measured irrigation, you're basically taking the watering can model and making it far more general and far more extensive in its application so that you can water all of the plants at the same time with the same accuracy as you would measure each plant using a watering can.
No more questions. Thanks again also for the question.
Thank you.